scalar projection and vector projection. So to start with, here I will draw two vectors, y, and here is the vector x. Yeah, this is a vector sign. For example, we want to project the x vector into y. And what we will do is to make a line that is orthogonal to y. And here is the scalar projection of x to y, which in this case we name it alpha. And if we want to represent it as vector, that is the result of vector projection, which here we name it P projection. To help with my explanation, we call this angle theta. To calculate alpha, the scalar projection of x to y, we can use the basic equation, which is the length of x multiplied by the cosine of theta. This equation, we can multiply it by y for both numerator and denominator. This part is the dot product between x and y. That's why the equation here can be written using the dot product in some books. They write it using the special bracket here. Or we can also write it as using a dot. I'm sorry, it should be x and y. Or using a dot here, x and y, which is equal to x transpose times y divided by the length of y. And all of these are vectors. To calculate the vector projection, P, we can just multiply the alpha with the unit vector of y. And the unit vector here can be obtained by dividing the vector itself divided by the length of the vector, which brings us to this equation. So here the length of y can be just make as quadrat, and then we times it using the vector of y. Now, using these two equations, I will give you example. For example, we have two vectors, v, which in this case is 2, 1. So here is 2 and this is 1. And we have another vector u that is equal to 1, 1. So the scalar projection alpha in this case can be calculated as u transpose v divided by the length of V. In this case is 1, 1, 2, 1. Then the length using an Euclidean distance, Euclidean length can be written as follow. And if we calculate this, 1 times 2 plus 1 times 1 is 3. And here we have square root of 5. And this is alpha, which is here. And this is the alpha is the length of this red line. To know exactly what is the point here, this point, we can use the vector projection, which is U transpose V divided by the length of V in quadratic, and then V itself. And because the dot product here is the same as above, we have 3 here, and the one that below here we can just quadrate it. So it's 5, and then the factor of V is 2, 1. And here we have 6 divided by 5 and 3 divided by 5 for the vector projection, which is also the same as the number here and here. Often we also need the distance between the U and P here. So if I draw here, is the distance between U and P, which brings us to the distance of the line here. And if we want to calculate distance between U and P, we can just use the Euclidean distance. So we have 1 minus 6 divided by 5 for the x-axis, and 1 minus 3, 5 for the y-axis. If we calculate this, this is equal to this, which brings us to 1 plus 4 divided by 5 quadrant. Yeah. So here we have the distance between U and P, which is equal to the length of the line here. Now we want to compare the result if we want to use the geometrical concept. Yeah, so the concept here, the geometrical concept, is usually used to calculate the distance between a dot to a line. For example, this is a line. I'm sorry, I cannot really draw a very perfect line, but this is a line that passes through the point 2, 1 here. And this is the dot that is 1, 1. So now we want to know the distance between this dot to the line here, which we need to figure out the value of the dot here, the position of the dot here. In this case, we need a projection concept because we want to use the geometrical approach. So first, we want to write down the equation of the line. In this case is, for example, this is x and this is y, and the equation will be y is equal to half x. Yeah, so if the x is 2, the y is 1 here. Yeah. And then, because we know this is a orthogonal relation, so if we draw a line here, yeah, it can be drawn better, but the line that is orthogonal to the equation y is equal half x will have a gradient of -2. Yeah, because the blue line have the gradient of half, so the magenta line have the gradient of -2. Now we put this gradient to a very normal equation for a linear equation. So here x and y, x1 and y1 is the line that is passed through the magenta line. So in this case is 1, 1. You can put it here. Sorry, is equal to m is -2 and x is like this. So now y is -2x plus 2 plus 1. Okay. So now we have the equation of our magenta line. From this line, we want to know where is the intersection between the blue line and the magenta line. Here I call the intersection as XP, YP. Here I call it that way. So to do this, we just plug in this equation, half x to the magenta equation. So in this case, we have and this is the intersection between those two lines, and we work on this will be and because we know y is equal to so we have here y is 3, 5. So we know here that the intersection is equal to 6 divided by 5 and 3 divided by 5. In this case, it's exactly the same as our previous result, 6 divided by 5 and 3 divided by 5. This method can also be used for a vector that is bigger than 2 dimensions. For example, if we have u in 3 dimensions and v also in 3 dimensions, I just choose an arbitrary number here. The projection of u to v can be written as all in vector, which bring us to and here is the length of the vector. And then the vector itself is in this case, we can just work on the equation 4 times 4 times 4 plus 4 plus 6 is 14. And here 16 plus 16 plus 36 is 68. And then we can just write it down like this. Of course, if you want the exact number, you can just multiply 14 times 4 divided by 68 and so forth. So this is the video about vector and scalar projection. I hope this helped with your understanding about projection. Thank you.